talk a little bit about the internals of Android. And before we do that, I'm just going to tell you a little bit about myself, for those of you who haven't met me before. So my background is in Java, so I don't have a strong C++ background, at least not for the last 10 years. So I've been doing Java before it was named Java, so from the mid-90s. And the last couple of years I've been extensively working on Android and Android internals. So I've been doing a lot of sort of poking around the internals of the operating system, building custom ROMs, etc., modifying the platform, as well as developing the applications. I'm also the author of the upcoming Learning Android book, which should be coming out next week. There's a sample, I believe, available somewhere, so you guys can take a look at it. But the book is also available in draft copy, free of charge at learningandroid.com. So you can get it from there. Again, it's a draft, so it's not the complete version. It's not the final version. I also frequently speak at conferences, such as this one. Also spoke at OSCON a couple of times, IEEE, ACN, and so on. Everyone got this? So let me tell you then a little bit about what we're going to do today. So we're going to talk about what happens when the system boots up, right? So how does everything get started? What are the bits and pieces that get started up? We're going to talk a little bit about the layer interaction, which I think is kind of important to understand for anything that has to do with internals. You sort of have to understand how the different bits and pieces of the platform communicate. And in the context of that, we're going to talk about the NDK, AIDL, and that's about it. So that should be what we can fit into an hour. So in terms of the startup of the system, what happens when you turn on the device is roughly this. So I'm gonna kind of walk you through this a little bit step by step. So essentially, as you guys know, Android is built on top of Linux. So we start a whole bunch of Linux daemons initially. And these are the low-level things that have to do with power management, memory management, radio starts as part of the daemons, etc. So these are some low-level Linux related things. They're not necessarily very much related to Android in terms of things that are provided on top of the Linux OS. So that starts up first. Secondly, what we're doing is we're starting up the runtime, and the runtime is basically a whole bunch of system services that have. We're going to talk about system services here as well, but runtime is basically their C counterpart, the native counterpart, right? So these are the bits and pieces that sit much lower to the kernel than these system services here. But they sort of go hand in hand. They're basically registered with one another. But before we can start the system services, which, by the way, the blue roughly correlates to Java. So things that is in blue, the blue boxes denote that it's a Dalvik or Java-based code essentially that's running. Before we can start anything that has to do with Dalvik or Java, we need a Zygote process. Zygote is basically a pre-warmed up version of any future application that is ever going to get started. So essentially, if you think about it, when a user clicks on an app, clicks on a little button, wants to start up an application, what happens is we need to launch an entire new process, right? One application essentially runs in a separate. Each application runs in a separate Linux process altogether. So we got to launch that process. On top of that, we need to load the virtual machine, right? Because we're going to need a VM on which we're going to load up our application. So all these things take a long time to execute. Memory allocation, etc. That's usually expensive. So to make things faster, the Android team essentially came up with something called Zygote. And what that is all that pre-warmed up and ready to go, right? So every future version of any application is going to have its roots in Zygote, right? It's going to be forked essentially from this process, and Zygote gives us that pre-warmed up virtual machine and the process and everything set up to go. So once we get Zygote going, which includes the VM itself, right? Once we have that going, we can launch system services. And system services are essentially bits and pieces of the platform at this point. So this is the Java code, right, or Dolby code. These are the bits and pieces of the platform that provide that rich application framework environment for applications, right? So for example, if you're writing an app and you want to play a music, or you want to find out your GPS location, or you want to find out what Wi-Fi networks are available, etc., you need to tap into specific services, right? So these are the services that are constantly always on, always running on a platform. System services. So that starts up next. We call them in Java, we usually call them managers, although they're backed by a service, right? So once this starts up, at that point we say the system has booted. So this is sort of the chronological line where we say the system is completed, the boot is completed, and at this point we can start the actual applications. So basically, like I have the line here, so this is the chronological order of things, right? Once we have all that done, we can launch our applications. So this is just any usual application that we may have running. So let me show you this in another way, on a little closer to the actual device. So I have an emulator running. Now I just booted it up, nothing really special about it. What I'm going to do is I'm going to do ADB shell to connect to the actual device, which in this case it's not finding. So this happens every once in a while. So you got to do ADB kill server. And ADB start server hopefully reboots that connection. This is where the tools are sometimes not perfect. So let me see ADB devices, and the emulator is back online connected to my laptop. So I'm going to do ADB shell now, and we're in. So at this point I'm connected to the actual shell of the device. If I do a PS to just see what processes we currently have running on the device, this is basically what we have here. So init process is just like on any Linux platform, that starts everything, right? So that's the beginning of life on the platform. Next, what we have, and you can sort of see the process IDs, everything. So it's chronological based on the PIDs. So next, what we have is a whole bunch of this Linux native daemons that get started. And this is basically where we're starting our runtime processes here, right? So these are now the Android specific runtime processes. So this is the service manager. This is, for example, the radio daemon, radio interface layer that's starting up here. And at some point we start up Zygote, okay? So that's basically correlates to this point in time here. So at this point we're starting Zygote. And the runtime is already started up. So once we have Zygote started, so these are also parts of the runtime. So this is also native code that starts up. This is our ADB daemon. So this is what's facilitating this connection back and forth between my laptop and the actual device. It starts up here. At this point, once the Zygote has been started, we can start anything that has to do with Dalvik code, right? Which also includes our system server. And so this is the system server that's started up here. You can actually see that the process ID, the parent process ID, is ID 33, which correlates to the Zygote process ID, right? So basically, that's where it comes from. Let me show you that like this. So basically, the systems this is forked over to this box to create the system server process, inside of which all our services or managers run, right? So this is where your location manager, Wi-Fi manager, connectivity manager, Bluetooth manager, telephony manager, all these managers basically they run inside of this box as a single process. So that's that. At this point we're done booting. So everything that follows after that is going to be the Android apps, right? So these are various Android applications that we have started up. So it's very much chronological as well in terms of what happens, in terms of the actual PS command, seeing the processes. The actual order of all this is in init.rc file, so that's where it's specified. But like I said, the order, it's very much important that Zygote starts before anything Dalvik related starts up. So any questions with just the boot up process so far? Yeah.
But how do you spell it? Init.rc file. Is there a period in there anywhere?
Yeah. So if you look at, so basically there's a file right here, init.rc file, and that's it's somewhat specific to Android. In a way that it's different than typical Linux distributions. It's very well explained in a text file in source. So I can actually show you this file really briefly. But what I'm going to do is I'm going to load it up from source as opposed to doing it from. So let me just load up my image for the Android source, and here's what I'm going to do: volumes gingerbread. I'm gonna open it up here, so you can. It's just taking a little longer to start up because it's loading all the directories. Should have actually. Let me do it like this. So in source, it's in system folder cd core. And that's where cd root there, and that's where our init.rc is. So let me see if I can open it up like this to show you. I guess my system is running a little slow. It will eventually open up the file. So this is the file that's basically specifying, the order of the startup order of things. So this is where we start up Zygote process, and it's critical to everything else. And you can also see that there are dependencies, that everything else is dependent on Zygote. So if Zygote dies, everything else needs to be rebooted, and that may or may not work actually. If you kill -9, for example, Zygote, so the system is going to reboot, but usually it doesn't come back up properly all the time. So that's a little bit about the startup process. Any other questions on how things how this starts up when it's How much does Zygote save in terms of the startup time? I'm not sure exactly how much it saves. I'm not 100% sure. But the key is to make the user experience as good as possible in terms of starting up the application. So that's what we're trying to help out. And the design of Android is such that we have a sandbox for each app, right? So each app is a totally different Linux process, unlike, for example, BlackBerry or some other systems where the applications are kind of separated in a Java layer. So here we're doing that separation in the C layer. So as such, we actually need a copy of the VM for every single instance, every single app, right? Yeah. Yes. So Zygote, yeah, it's a C. Exactly, it's a C process, but it is going to load up the instance of the VM, so that when you fork it, you basically have the VM ready. Yeah.
Other than the QEMU daemon, what differences will be there between an and
not many. I have my consumer phone. We can just kind of that is totally non-modified regular phone. So we can compare the notes with that as well. So now if I connect my physical phone to this, I'm going to do adb-d shell to connect to the device shell, right? And I can do a PS on this device. And as you can see, it's pretty much very much similar, right? So init starts everything, a bunch of daemons start up. They're slightly different, right? So there are different sets of daemons, and that has to do with things that are sometimes proprietary to the device. So there's going to be a lot of driver-related stuff. It's the whole world that is I'm not that familiar with. But but at some point we're basically starting up our service manager, which is the C part of the Android code that backs all the system services, and we're starting a couple other things. But here again is Zygote starts up, and after that we start everything else. So you can see that PID is the parent of the system server, right? And once the system server is done, this is when we actually completed booting. This is where we send a broadcast message and say boot complete, or in broadcast intent. And at that point, we're starting up everything that has to do with Android. So these are all the Android apps. That's what I'm referring to. So I have quite a few running in there. So it's very much comparable in terms of that. Usually the init files are going to be quite different. Not quite different, but they're going to be different. But that's usually done on the platform in a way that, let me show you, what's a good way to show you? Let me show you on the actual, sorry about that, on the actual system. So ls, so init, in this case I only have one init, but on this, on the emulator, we actually have two inits, right? So this is basically the init RC file that is specific to the emulator. Goldfish is a nickname for emulator. For some reason, they're always named after fish, so there's trout and so on. But Goldfish refers to the emulator. So this is the emulator specific init gold. Let me cat it. And you can see that this is where we're setting certain things that are emulator specific, such as, for example, what to use for its internal IP address, that battery level, things that kind of like, it's always at 50%, and so on and so on. So this is all set in that specific Android emulator specific RC file. So when it's, yeah.
I understand that you explained the side of the startup time of the Android, but how come the emulator takes so long to start up?
So okay. The question is how come the emulator takes so long to start up? So what we're speeding up. So let's draw the. Let me hide this because it's not working very well. So let me draw this line here, right? So this is where we say the system is booting up, right? You're saying that this part here is relatively slow, right? And but that's not what we are trying to make faster. That is not our goal. Our goal is to make startup of this faster. So that's why we have Zygote. We want to make this start fast. It's not a big pain point for the user that the phone boots up really slow, right? Because you boot it up once a week or something, right? But it would be a big pain point if starting an app takes a long time, right? So for example, iPhone fakes startup by putting up the photo of the app, the image of the app, while it's actually cranking the background and booting up the actual application. So in Android, we focus more on actually making things faster for real, as opposed to faking it. There's a question? Yeah.
Yeah, I think what I thought the question was is why is it that the emulator starts taking so long to start?
Why does the emulator take?
What's the emulator doing on such a powerful machine that it takes forever to get going?
So why is the emulator? So that's not. So why does this part here take a long time to start? So keep in mind that we're using an emulator, not a simulator. So I keep telling people, they sound very similar, but they're quite fundamentally different. So this here is a virtual machine, right? So we are running exactly the same code base as we are running on this, right? So it's ARM-based code and so forth. So we're not simulating anything. So the fact that I have a dual-core, 8 gigs of RAM MacBook Pro doesn't really matter. I'm running the same code base as I'm running on the physical device. Now, why it may be slightly slower than on physical phone is purely because of the emulation. So whenever you emulate things, you're interpreting the binary code base, so that runs a little slower. But we're gonna do some testing on speed later on with the NDK. So we're gonna see if we get some fundamental differences between physical phone, emulated phone, and so on. So So when it's all said and done here, when we finish booting up, we basically have this, right? This is the stack. Many of you have seen this picture before, yeah? So at the end of the day, everything is up and running, looks like this. So at the bottom of it all, we have Linux, right? It's backing the native libraries, which are basically C, C++ code that is there to back this part of the system, right? And at the end of the day, application, developers write apps, right? So as an application developer, you want to write an app that's going to talk to something that's available to you in the application framework. That's why Android is so appealing, right? Because you have this rich framework, you can just tap into it, you can, get things done quickly, like, for example, figure out your GPS location, etc., etc. Now, for the framework to be able to get a job done, it needs to talk to the libraries, right? It needs some kind of backing from the native code base. And those libraries, in turn, then sometimes need to talk to the actual hardware by connecting to the the drivers and things of that nature. So that's just how what the stack looks like. That's our standard sort of Android stack. Now, what I want to get into is talking a little bit about the interaction between the various layers of the stack. So what's interesting to us, so this is not a conversation so much about writing apps, right? That was the talk yesterday. But what's interesting to us is how the various parts of the system actually communicate across these boundaries, right? Across these various boxes. And keep in mind, while my stack looks really nice here, right? Everything is like ideally sort of segregated and put in compartments and such. When you look at the actual source code, it's not quite like that. So things are much more mixed together. So the picture looks nice, but it's not like that on the code base. So what happens is, in terms of this interaction between parts of the layer, different parts of the stack, is we essentially need to cross a couple of boundaries, right? So on one hand, this part here of the stack is mostly Java, all right? And this part of the stack here is mostly C code. So one boundary that we have to kind of bridge is this one here, right? The second issue that we have is when we want to have one application talk to another application. Remember how we said in Android each app is sort of an island on its own, right? It's a separate Linux process with its separate UID, separate permissions, everything separate, right? So if you want to have one application talk to another application, we basically need to be able to communicate from one process, so I'll call it process 1, to another process, I'll call it process 2, right? Okay, so those are sort of the two main boundaries that we kind of got to understand how to bridge, because everything else is boils down to Java and C, which presumably you guys know. So I'm not gonna worry about that too much. But what's interesting to us is how to make this communication across the world of Java and the world of C, and process 1 to process 2. So that's where the layer interaction basically comes in. And there are different ways to do that. And what I'm going to do is I'm going to just show you a couple of scenarios for a couple of different frameworks that exist in the system right now. So this is courtesy of source.android.com. And the actual what's in the boxes doesn't really matter that much. Don't get stuck on details too much at this point. But basically, for example, this is the audio framework. This is how you write an app. You say, I want to play a song, right? Like I want to play a little, music. And what happens next is your code is probably interacting with the media player, which is what you would find in the application framework, right? That's what you program against. That's what you use. Now, this is the world of Java. Now, to cross over to the world of C, we use something called JNI, Java Native Interface, right? So that is basically our bridge to the world of C code, which is basically everything below roughly this line. And so media player is communicating to a media player counterpart in C. So this would be the C implementation of that of that code, basically supporting the native methods in the Java code. That in turn may load up some libraries, the C libraries. That in turn may then communicate eventually to some kind of audio driver. So, so what we're using here is basically we're using JNI to cross from the world of Java to the world of C. Okay, so this is just one scenario, right? So another scenario is the camera and video framework. So it's a little more involved. But basically what I wanted to point out here is that unlike just a playing music, which is more or less just a set of libraries, when it comes to, for example, camera, we actually have a camera service running. So camera service is now example of that something that is running in a totally different process, right? So we have now the problem of bridging process 1 to process 2 communication, right? And what we're doing in this case is we're using something called a binder IPC mechanism, binder inter-process communication mechanism, to go from one process to another process. Okay, so that's basically the Android specific way of doing that. Of course, you can do, you can just open up a socket. There are many different ways you can communicate between multiple processes. But what Android brings to the table that's sort of new is the binder IPC mechanism. So what that looks like now, basically, let me show you on the big stack picture. So basically, what we have here is we're going to have the binder to bridge this, and we're going to have JNI to bridge that, right? So that's essentially what those are the two tools that we have at our disposal when it comes to working with the entire stack, with looking at all the bits and pieces of the stack. Does that so far make sense? Any questions on that? Yeah.
Is binder only at the Java level or
I believe it's in the C level as well. Yeah. We're going to do an example with the Java version of it, but the binder is implemented in C. Yeah. So let's start. Let's start then with the JNI. How many of you actually used JNI before? Okay, most of you. All right. So great. So JNI is basically a Java native interface. It's just a Java thing, right? It's nothing more than a convention on how we're going to name things in C so that Java knows how to call it and how we're going to call from C back to Java. So essentially, it's just a naming convention to facilitate that. What's important to kind of understand is that JNI code, in other words, your C code, native code, still runs on top of the same Java virtual machine or the same VM that your Java code runs on top of as well. So this is what you would typically do when you're doing something with some JNI code. There's nothing really Android specific in here, right? So this is just a plain old Java. So you write Java source code, you compile it, you get a class file. That class file goes on top of the virtual machine, and that's where it gets interpreted. If there's anything declared native in that class file, you compile it with Java H -JNI, which is the tool that comes with the JDK, right? And that produces a header file. This is your .h file. And then what you do is you implement that header file in C. You link everything, you compile it, you get your dynamic library .so file, right? And that dynamic library gets eventually loaded by the VM. So essentially, when Java wants to call C or C wants to call Java, it doesn't work like this. It actually works like this. So the Java code goes to the VM, and the VM loads the library and talks to it, right? So that's sort of how it happens in the world of JNI. Yes, yes. So for our purposes, so far everything is the same. Yeah, in Dalvik and in Java. So I'm kind of using those terms interchangeably because there's nothing really too specific about it. So. Which tools? Java. So Java Age is just a standard Java tool. There's really nothing. So that, as I said, it ships with the JDK. So you guys should have it as part of JDK, Java Development Kit. Yeah. So far this is just a plain old Java. Now the next topic is basically something called the Native Development Kit. Anybody played around with NDK? A couple of you. Cool. So NDK brings makes life simpler. Brings a couple of things to the table. So here some things that NDK brings to the table. So for one, it provides the entire tool chain to compile your code, right? So when you're compiling your C code, you are compiling it for the platform that the device platform. So in other words, ARM most likely, right, or x86. So setting up those cross compilers can be very painful. I did some of this before NDK got released, and it's one of those things that takes a lot of time unnecessarily. So NDK solves that entire problem by providing the tool chain nicely packaged. Secondly, what NDK also provides is a way to package the libraries with the APK file itself. So, in other words, if I don't know if you guys noticed, but in the init.rc file, which let's see why it's so slow. Okay, in the init.rc file, we specify at the top the environment, and the only thing that we have in the environment in the LD library path is the system.lib folder. Oh, there's also the vendor lib, but that's besides the point. So system.lib folder is the only place. So in other words, if you look at the file system of the device, which I'm just gonna pull up here. So if I look at the device file system, this is the only place where this is the place where all the SOs go, all the libraries. Now the problem with this place is that it's on a read-only file system, right? So it's not a problem if you're building a custom ROM, you can easily put stuff in here. But if you want to have a native code that ships with your application, this is not a place you can put it. So that's the problem. The solution to that problem is to basically put your library alongside with your application. So it basically goes into the app-specific sandbox file system directory, right? So each app, as you probably know, has a /data/data/ its sandbox. So for example, I think this is the one that I'm using right now. So this is the sandbox for this particular application, and the SO file goes into this folder, right? So that to me that's a big deal because it solves the distribution issue. So now you can put your native code in your app, and you can distribute your app through the market to everyone, as opposed to having to create a custom ROM to distribute your code. So that's a big deal. It also provides a set of header files that are standardized, and it also provides samples and the documentation for that. So in terms of the NDK, why would you care about it? Why would you use it? Right? We're still talking about the application development with native code. So why even go into C realm? So one of the reasons, the main reason for that is performance, really. NDK is sort of developed, in my mind, with the motivation to support games, right? So that's why a lot of sort of standard headers have to do with, for example, math, graphics, that sort of stuff, right? So it's really for things that are computationally intensive. People use it for different purposes as well. You may have legacy code, some C libraries that you want to include as part of your project, and you just don't have time to convert it or don't have interest in converting it to Java. So in that case, you can just basically wrap it with the JNI interface. So those are some motivations. Keep in mind that your SO library is still going to be sandboxed inside of the same process as the rest of your application. So having something in C, C++, it doesn't mean that it's going to be able to accomplish from security standpoint anything more than Java can do, right? Yeah. So what about the Flash plugin? I'm not sure. You could put your library on the SD card if you want to manually manage where you put the library and then load it from that place. So you could basically manually manage the location of files and load them, explicitly. But what NDK does is sort of removes that responsibility. You don't have to worry about it. You just create a library and you're done with it. Yeah. So that's basically the motivation for NDK and why you would care about that. So the steps to using NDK, I sort of outlined them here like this. So basically what happens is you write some kind of library, your Java library, and you may leave certain methods declared native, right? Meaning you're not implementing them in Java, you're just saying, hey, there shall be a method implemented somewhere natively. You compile your Java, you get your Java class file, no big deal there. But then what you do is you recompile your class file or you apply Java age to your class file to get the header file. So this is, again, your .h file. Now what you do is you implement that in C. So you write C code to implement the actual header file. You create a make file and you compile everything into the .so file. So this is now dynamically, this is now linked from Java to the SO, right? And then you write your application that actually uses that. So the application is no longer concerned with the fact that some parts of that library are actually implemented in C. Yeah. So about the sandboxing. So this is the this would be the process, right? So so this is an application process. It's got its own like library. It's got its own the Dalvik virtual machine. It loads what I call the building blocks or components. So these are your services, activities, providers, receivers. So all that is part of your application context, right? Your application. So
the library is running outside of Dalvik, yeah?
well, it's the Dalvik. So Dalvik virtual machine loads up the library, right? Just like the Java virtual machine loads up the library. So that's it gets loaded by the VM. So VM actually communicates to the library. So the VM is the one that resolves your calls to native. So when my Java code says I want to call native code, the VM actually resolves that to the actual C++ implementation of that. Yeah. So we're going to see this in code shortly. So this is basically the steps, sort of like in lines and circles. So here's what I'm going to show you an example that I typically build, and it's basically I was looking for an example that I can really quickly do both in C and Java, something that has a very simple algorithm and something that kind of gets slower, really quickly gets really slow, right? So Fibonacci is perfect for that. So Fibonacci, again, is just Fibonacci of 0 is 0, Fibonacci of 1 is 1, and then it's a recursive formula. So Fibonacci of n is Fibonacci of n minus 1 plus Fibonacci of n minus 2, right? So it gives you this kind of sequence. So what I wanted to do is I wanted to build an application, and I wanted to basically use both algorithms and see what the speed difference is. And these are roughly the steps, but let me show you that in code instead. So I have this little, hold on, let me close, let's start like this. So I have this little application here, and typically what I would start with is writing the Java library. So this is just a plain old, Java code. It's got nothing Android-ish in it, right? So I have this is my simple implementation of Fibonacci in Java, right? Recursive. I also included everything that can be done recursively can be done non-recursively as well. So this is one of the iterative implementations of the same algorithm, right? So that's basically my Java code. Now for my native code, what I did is I simply said I declared it, here, and I said it's native. So in other words, look for it elsewhere, right? So my native version of the Fibonacci is recursive is declared here, and the iterative version is declared here. I also need to make sure that I load the library where this is actually going to be located, right? So that's the first step. That roughly corresponds to this here, right? So we wrote the native library and stuff, right? So now what we need to do is we need to use Java age-jni. Now this is one of those things that Eclipse is not automating these steps yet. I know people are working on that, but so we kind of have to do a couple of steps manually, but it's not too bad. So what I'm going to do is I'm going to go to my command prompt, and I'm going to go to my workspace Fibonacci. I'm going to go to the bin folder, right? because that's where my class files are. So from here, instead of changing the class path, so from here I can say Java h-jni, and I can say I wanna apply it against that class. So com Maracana and then fiblib, right? So what this tool does is it basically analyzes the class, and anything that's declared native, it takes that into account and creates a corresponding header file. So what we got here is this file, the header file. Right? Now this header file doesn't really belong in the bin folder. So one of the ways that I usually organize this, and it seems like everyone else does as well, is create a JNI folder that hangs off of your project. So this top level JNI folder, and put all the C native related code in this folder. So I'm gonna cd into that. I'm gonna actually move this file. So com_to JNI folder. I'm gonna cd to JNI folder. And so that's where we have that file now. So that file looks like this. So this is their standard JNI file. And let me refresh it. So this is that file that got automatically generated. The only things that you really care about in this file are these signatures, right? So these are the method signatures that correspond to things that were declared native. So in other words, when we said here, I want to have fib_n for fib native be declared native, right? So the JNI noticed that this method is going to be declared native. Since this method is in a class called com.maracana.fiblib, right? And the method name is fib_n, that's why we have such a long function name now. So it's java_com_maracana_fiblib fib_n, right? And these are the standard exports. This is the return type. So JLong. So basically, JNI standardizes on the types since C doesn't really have a standard. So just to align it with the Java primitive type size. And so this is our return type, and this is our input, the n that we are inputting into the function. Now these two variables are always going to be there. Basically, JNI env refers to the environment itself, in other words, the virtual machine. In JClass, which could be JObject if I had it non-declared static. So the fact that I have it declared static gives us a reference back to a class as opposed to the instance of a class, in other words, object. So this second parameter is either going to be a JClass or a JObject, in this case a class. That refers to the class that called it in the first place, right? So that's basically the signature that got generated by JNI Java H tool. So at this point we have the header file, right? So we didn't write it; we just got it auto-generated. Our next job is to basically implement that header file. So we're only writing these files, right? This is the only things that we're really implementing, and also, of course, something that's using it. So the C code for this, the C implementation of this is fairly straightforward. So what you do first is you make sure you include that header file, right? And then you basically copy paste the signatures of your methods. So there's my method 1 and function 1, function 2, right? And then you implement. So in this case, I'm implementing by calling the local functions, which is basically the copy paste of the same algorithm as we have in Java, right? So this is our Fibonacci, just Fibonacci recursive here and Fibonacci non-recursive here, right? So it's the same code, right? We're going to run the same algorithm both natively and in Java. So at this point we have the C implementation of those things that were declared native. So the only thing that's missing is the make file. The make file looks like this. I usually just copy paste it from one of the samples that come with the NDK. So that's simplest way to create your make file. Alternatively, if you want to read about make files and so on, I'm not sure if I'm online, but source.android, I'm not going to do that right now, source.android.com under porting, there's the build system is explained, and there's a link for, there's a cookbook that explain, gives you common make files for basic stuff. So that's another place to kind of look at how to put it together. So once you have basically the header file, its implementation, and the make file, all you have to do is you have to build it. So you do that by simply doing ndk build, and that's going to take the make file, read it, compile everything, and create the SO file. So this is the cross compiler, and everything happens in here, right? So this is dramatically simpler than if you were to set up your own tool chain and worry about all the details of compiling all this. So ndk build just does a lot of good stuff behind the scenes. Yeah, I just learned about that. So the Moto dev team apparently created the integration for ndk into Eclipse. And right now it's available as part of a Sequoia project, which is a separate download into Eclipse. So you guys can look it up. So I haven't played with it, but apparently it does a lot of this sort of manual steps that I outlined here. It's been on. So at some point it's going to be Control-S to save it, and everything gets rebuilt as well, just like Java does. So yeah, that's great. So at this point, what happened is we basically got the library directory created here, and so this is new. So this is the output of ndk build. There's also the obj folder, which is the intermediary files, but the final library is right here. Right? So when we push this application, when we install it onto the device, like as you saw it ends up in the /data/data/your/app/libs folder, right? So that's where it's going to be located. So what I'm going to do next is I'm going to run this application. I also have the activity that goes along with that. In other words, something that uses this code, but I'm not going to discuss that because it's not really a topic of this conversation. It's how to write applications, just a standard activity. So I'm going to run this. I'm going to run it on the emulator first. And let me rotate it so that it fits better. Let's see if it's going to... Okay, so it's coming up. So I have it here. So basically what I can do is I can enter some kind of code, some number for my Fibonacci sequence. We can start with something small like 23. Click on go, and so these are the results that I got. So basically the Dalvik recursive version took about this is the result, which should be equal, right? And it's not interesting to us too much. But what is interesting is the actual time. So what we're comparing is the Dalvik recursive to native recursive, right? Yeah. So that's one interesting number, and the second interesting number is this number here, which is basically the iterative version of Dalvik versus the native iterative version of the same algorithm, right? Yes, so I timed, the iterative algorithm is substantially faster, so if you time it in milliseconds, you're going to get like rounding errors. It's going to be like either 0 or 1. So I changed it to nanoseconds.
The first one's micro? Or
the first one is micro, so it takes a long time, right? So now what we're really looking for is the order of difference, right? So this is about, these numbers are the same order, right? 62,000, and actually they're not. They're different. Versus so apparently it's slower to run it. Yeah. Let's go with the number. Let's go with a large number like 25. So this is what we get. Right. Yeah, so the numbers are, the nano timer is not as precise, and we're going to get much more of a difference between the iterative versions. But what's interesting is for the recursive version, we're consistently going to get about one or the order of a magnitude difference, right? It's going to be 10, 20 times slower, yeah.
yesterday when I was
So Dalvik is registry-based, not stack-based. So it actually doesn't work very well with stack-based applications, which recursion is. So it's actually the opposite. So my understanding is that if you have a code that uses a lot of recursion, you're not going to get a good performance from Dalvik, and it's also not something that a just-in-time compiler can kick in and optimize and help out with, right? So that's my understanding of it. Now, when it comes to iterative, the just-in-time compiler can actually optimize your code, and the performance is going to get about the same, right? Very quickly, but there's obviously a certain cost involved with JNI bridge as well. So that's why native version may actually appear to run slower, just because we're timing it from Java, we're timing the actual bridge over to native, and then the results back. So, so those two are sort of the toss.
The time you spend in native has to be worth your while.
Exactly, the time spent native has to be worth your while. Yeah. So does the NDK build put the lib into the APK? No, it doesn't. It simply puts it into the libs folder, and basically when your APK builder is going to put it into the APK once I hit run button, right? No, the APK builder doesn't. So there's that's basically a naming convention. So this folder libs is supposed to be the way it is. So if this folder exists with this naming convention, the APK builder is going to look for this library and it's going to place it in a proper place. That's basically the platform that we're. So in this case, we're building for ARM EABI. Exactly. So that's a good point. So see, for example, when we install it, so if I built for x86, presumably I would have a different subdirectory here as well. So since we have a native code, we may have multiple versions of the lib.so file, right? And then the proper version is going to get installed. Is there a tool like Traceview for native code? Not as part of Android. So Traceview is driven by Dalvik. So the information actually comes from Dalvik. It doesn't come from. So we don't. The C code is a black box in that case. So Traceview doesn't allow us. So it treats native code as black box. But I when I used to do C programming many years ago, I remember there were tools native to C that would do that sort of stuff, profiling. So, but not that I know much about that. So the question is, you have the SO, you install the app, but the lib doesn't seem to be there. Install it again. I'm serious. I just did that. I was a couple hours ago when I was preparing for this, and I started from scratch. And I was like, wait, what just happened? Why is it not there? And exactly that thing happened, and I just ran install again. And the second time around it worked. Native code debugging, GDB is there. There's a ADB supports GDB bridge, so you can use that. So if another application wants to use the same lib file, and presumably that's not an application that is written by you, so you can put it in the same context. In other words, if you have two applications that you sign with the same key, and they live in the same package, then they can share the lib file. But if they're totally separate applications, then the lib files are off limits, because the lib files, the libraries live in their sandbox parts of the file system. So yeah, they're off limits. Yeah. So in terms of the NDK compatibility, as long as you stick to the libraries to the headers that are guaranteed to be supported, you're fine. Right, so that's part of the, that's part of the what NDK is. It basically says these header files are going to be supported for a very long time, right? You could be using some other libraries. For example, people used to go directly to BlueZ library before Bluetooth was available as a Java API, but that's not really guaranteed to be around for forever. So. What I wanted to do is so this is one part of the equation that I wanted to cover with you guys, and that's basically building a. By the way, I'm running it for a Fibonacci of 33 just to see what number we get, and that's the number. So I believe. So. Oh, right now. So keep in mind that I'm running all this on the UI thread, which is a big no-no, right? In a big final application. and we discussed this yesterday, so they should be running in async task. It'd be a perfect candidate for that. So that way, we would have, we could run for much larger numbers, and we would not get the ANR, right? Application not responding. But that's a different conversation. We talked about that yesterday. So this is going to take some time to process. 33 is about the limit that I can push this without the ANR coming through. So let's see. Is that the number? Yeah. So that's the number. So 35 seconds versus 1 second, right? And what's interesting is when you turn on trace v on this and actually analyze the execution, you can see that there are a gazillion recursive calls happening in Java, and that's basically what's taking like 99.8% of time or something. So that's where it's slow. The second piece of the equation. So we talked about, right. So what we're discussing here is how to bridge those two divides, the divide between Java and C, and we saw that. Now I want to briefly talk about how to bridge this divide, which is basically process 1 to process 2 communication, right? So one of the tools that is available to us is something called the binder IPC, right? And the access to that is via the Android Interface Definition Language, or AIDL. So basically, a binder is our system for doing the IPC calls, right? So if I have one application, say for example, this is my my application that wants to know what its GPS location is. So this application would say, hey, I want to get the system service for location. So it gets the location service, right? Reference to it. And then it would say location service, what's the last known location, for instance, right? So that call goes through the binder driver and gets marshaled then to the appropriate service, right? For the service to execute, and then it goes back and this way back to the application. Okay. Now, what's important with the IPC mechanism is that it's a blocking call, right? So it's a synchronous call. Unlike intents, which we discussed yesterday in the workshop, which are basically asynchronous, right? So they go and they get placed in the queue, and then the looper picks them up and so on. So it's a different mechanism. So this is a blocking call communication. So what I have here is I just wanted to show you an example of how this application, how to do this. So what we're going to do is we're going to create a service, an application here, which is going to be a service, and it's going to be a simple logger service. So you're going to basically say, hey, log something for us. It's a remote logging service. That's all it is, right? So we're going to have a simple client that is going to make that remote call to the logging service to log something, and and that's it. Come back once it's done with the logging, right? So these are going to be two separate processes living in two separate VMs. Yeah. What are the limitations for the binder in terms of the moving the data across? I'm not sure what the limit is on that, but if you're moving a lot of data, maybe the binder, maybe the IPC is not the right thing, right? Because the other tool that we have at our disposal are the content providers, and they are sort of designed specifically for dealing with data across the boundaries, application boundaries. So let me show you this example here. So I'm going to close all this. So first of all, I'm just going to run it first to kind of show you what it is, and so you can see it. So this is a simple little app that is going to log remotely. So on one hand, I have, starting up. On one hand, I have the client, and it simply has a button, right? And as I click on the button, this is going to make a remote service call to a service. Now, service we can't really see. So for that purpose, I'm going to basically run the ADB logcat here. And let me see. I'm going to disconnect my physical device in this case. So this is my logcat. Not much interesting stuff going on until we press click, right? So click, 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 and that's basically logging that something is going on, right? So we can see that that there's a message, and we're going to look into this code, how this works. Another interesting thing to notice is that if I do ADB shell PS, you can see that we actually have two separate processes altogether. So they're totally non-related to each other. They're two separate applications from two separate people and two separate packages. They happen to be signed with the same key, but that's not very relevant. In every other respect, they're separate apps, right? So the client and the servers. So typically, what you do is you start by defining your interface for the remote something, and so that is hold on, it's trying to open it in TextMate versus open it here. So that interface looks like this, and it's basically this is basically the AIDL code, and AIDL is essentially inherited from IDL, which is the Corba interface definition language, right? So in many ways, it's very, very similar, but it's also very similar to a Java interface, as you can see. So in this case, what we have is we're defining the package. We're basically defining, let there be an interface. We call it ilog service, and it's got two methods, logd and log. The reason why I put two methods is because this one is only using primitive data types, which makes life very simple, right? So string is sort of a primitive data type in this context. So it's fairly simple. Now, this is where things get a little more complex because I now have a proprietary, I have a custom object that I want to send across the process lines. Well, if you have something like that, you actually have to create this object as a parcel. So it needs to be a parcelable data type that can actually be, sent across the wire from one process to the other. So that's why I sort of have the second example just to kind of demonstrate that. And that's going to be in this IDL file called a message. So let me briefly show you. So defining the actual custom data type message is fairly simple. It's fairly simple because you just basically say let it be parcelable. Yeah. Now the Java for it gets a little trickier, but we're gonna get to that later. So what happens when you add the AIDL files? There's actually integration for this in Eclipse. So Eclipse is automatically going to run AIDL tool from the SDK and process this file, the interfaces, and create the stub files. So this auto-generated file that's extremely ugly is an auto-generated code, right? By AIDL tool. So that's what that looks like, and you don't really care too much about what's inside of it, but basically that's what's doing the marshalling and unmarshalling of data back across to the binder. So you don't typically look at this file too much because it gets dizzy. Now, what we need to do is we need to provide the implementation of a service. Yeah. So we're not defining an interface. We're simply declaring a message as a parcel. Now the Java for it is going to be interesting. We're going to get. If you use a class that's a custom class, no, you have to declare it parcelable, and you need to then provide a implementation of it. I'll get to that next, but I want to show you just how the service works. So to implement the remote service, so remember, I'm not sure how you guys use services, but in most people use services as in Android as unbound services. So in other words, the onbind method is usually something that we ignore. We usually focus on start command, on destroy, right? So those are usually the methods that people implement, like for example in a music player application or something like that. So that's an unbound service. In this case, we're implementing a bound service. That's what the IDL basically provides. So what that means is we need to provide the implementation for onbind, and we need to return a binder. That implementation is really the stub for that implementation is provided by that auto-generated code. Right? So you basically just say, I want to return that, and that Eclipse is actually going to fill in this for you and give you all the methods that you need to provide. So you essentially just need to provide the meat of the actual function or method, right? So you need to say what happens remotely, right? So at the end of the day, you're just filling in this piece of code and that piece of code, right? Eclipse is going to create it. You already have the stub auto-generated for you, and Eclipse is going to tell you what you need to implement to implement all the unimplemented methods. So that's what the remote service looks like. This part is fairly straightforward. Now, and you also need to, of course, declare it in the manifest file to say, hey, you know, this is going to be a service, and it's going to be available for other people to bind to it. So that's what we're doing here. We're declaring it here, and I'm basically creating some kind of action for which this service is going to listen for. So this is how clients are going to bind to that service, and this could be any piece of text that you come up with, but this is pretty standard to use the actual full-fledged name of the interface. So once we have the service done, the next part is to do the client. And for the client, what we're doing is basically we're copy-pasting the same IDL. So these are my IDL files because the client needs to know the same needs to know what the interface is to the service. So that's why we need the IDL. And then what we're doing in the client is we need to connect to that remote service. So this is where things get a little interesting. So what I'm doing here is I'm basically creating an intent that defines what we're going to connect to. And I'm saying bind to that service, bind to that remote service, right? But what's important here to know is that this happens asynchronously as well. So this bind is going to finish really quickly, but it doesn't mean that we're going to be actually bound to the remote service at this point. As a matter of fact, we're not going to be bound until the next iteration of the looper, right? Because the looper is actually going to just pick up the next job at the next once it's done with this to actually do the binding. The results of the binding are then communicated back to us via this service connection class. So that's what this service connection class is. So you basically need to provide a class that implements this interface that simply says what happens when we got connected or when we got disconnected. Okay, because this is asynchronous. So this is something that people usually sort of don't get, because if I was trying at this point to communicate directly log service.log, for instance, right, this would fail because we do not have log service bound yet. Okay. I'm sorry? No, it will. It's guaranteed to fail. It's 100% is going to fail. So that's because keep in mind that I was showing this picture yesterday. Keep in mind that how things happen inside of the system. So inside of a system, we have something like this, right? So this is our process, and so we have a single looper on a single thread, right? And this guy is doing jobs serially, one job at a time, and it blocks. So while it's processing that method, I think that was on create that I was in, right? Was I in on create, right? So while it's processing this job here, it's not processing any other job. So the fact that this job says bind to a service, so we're inside of on create here, inside of the looper, that says bind to a service, but that's merely going to generate a new message on top of the queue for the next time around to do something. So it needs to actually finish on create first, be done with it, go back to the queue, pick up the next job, which says bind to a service.
Is this ever multi-thread?
So is this ever multi-thread? You could have, yeah, you could have multiple threads, right? But again, we have it's still going to be asynchronous, and it's still going to be on somebody's queue, and there's still going to be a looper processing that looper's queue, right? So you could have multiple threads, but that's not going to make this.
Multiple threads waiting on that message.
No, you have a single thread. You have single looper per single thread.
Okay, so the queue is not ever protected. Is that your observation?
So these are basically one-to-one. There's a one-to-one relationship between a looper and a queue, right? So yeah. So that's basically, so at that some point we then bind, and at that point log service is finally available. This is the first time that the log service is available. In the log service, what happens when on a successful bind, you're going to get back an iBinder. That's the binder that we are returning here as when we say return the stub, right? We are saying return new log service stub. So that arrives here as an iBinder, which we now need to cast to our particular service. And for that, again, we use that stub, that auto-generated code. So it gets a little confusing on a client side just because of this asynchronous nature of the actual binding process, right? Most of us as app developers, we're used to using system services, and you just say get system service, and you get the system service, and exactly the same stuff is happening. The difference is that the system services are already bound to the context, so you don't need to actually do the bind, right? That's what the difference is. I think there's a presentation tomorrow specifically on system services. I think it's going to be more on the lower level stuff. Yeah.
It looks to me like your implementation here is only going to let you log one thing. Is that true? Because you didn't have to put the log. Oh, okay, I'm sorry.
I have on click here, and I can log as many times as I want,
I
right?
saw log I, and I thought that was the client call to the.
Yeah. Logs, we can call log service as many times as you want. One thing that I didn't talk about is the message. So the actual message.java, as I said, needs to be parseable, right? To be able to be something that you can send across the wire. And if I have a simple message that contains a string and a text, what that really means is you need to provide a way to read a parcel in, right? And you need to provide a way to write a parcel out. So basically, it's kind of like a serializing in Java, but not really, right? So you're basically converting a live object into a stream that can get also created on the other end. So that, and you also need to provide this creator as well. But in a nutshell, you need to read it in and write it out to be able to make it a parcel. Yeah.
So you can try where this is possible in Java to still need to create the AIDL file.
Yes, you still need to create an AIDL file. Yes, in the interface.
Another question is in your I wonder why do you need the action intent filter on the service because you're using explicit intent.
So the question is why did I even need to define this here as an action? Why didn't I just say build an intent and spell out the name of the class? I wanted to provide that clear separation that I have no intricate knowledge of what that class is and so forth. So that's why I would not use explicit intent. I'd rather use an action-based implicit intent in this case. Yeah, yeah. Is there a way to keep people from running your service? Yes, you can add permissions, right? So you could you can require the caller to own a permission to connect and so forth, right? Yeah. So can you dynamically choose the implementation of the interface? Yeah. Well, you could, but you would have to write. You would have to create a factory method, I guess, yourself, right, to provide that. There's nothing dynamic automatic about that. So binder is using shared memory to make, so that's why it's making things supposed to be much faster than it was copying, yeah.
How would I then, because I know that there's like a memory.
It's, you know what, so if you guys go to learningandroid.com, this is basically chapter 14 and 15. And so it's, what I try to boil down into, so that's outlined there, all the code is there. I'm going to make these 3 applications also available for download here. So on this forum blog post, so I'll make the code available. Yeah. If you have any questions, I'll be here. But otherwise, thank you and have a good lunch.